Hello everyone, and thank you for listening to this presentation. Today I'll be presenting our work entitled ACING, Actor-Critic for Instruction Learning in Black Box Large Language Models. This project is a collaboration between Fourati, Marco Canini and myself, Salma Kharrat, all from KAUST University. Our motivation stems from a key question in the field of large language models, which is how can we optimize prompts or instructions for models whose internal parameters are inaccessible. And in this work, we approach the problem from a reinforcement learning perspective, framing instruction optimization as black box optimization task. Let's start with a surprisingly simple example that captures one of the core challenges in prompt optimization. It all comes down to this. The way you frame a question can completely change the result you get. Here, the goal is straightforward. Actually, we want the model to take a word as input and output its antonym given an instruction. Now, look at these two instructions. The first one, written by humans, says, write a word that means the opposite of the input word. It's perfectly clear, right? Then comes the slightly rephrased version, take a word and change it to its opposite. And boom, accuracy jumps from 70% to 82%. That tiny change, just a few words, makes a huge difference on how the large language models understand and performs the task. And that's exactly the kind of sensitivity that makes prompt optimization so fascinating. This is actually a fundamental issue in prompt engineering. It shows how sensitive these models can be and how much time can be wasted just manipulating words, trying to discover that one magical phrase that works best. The difficulty of solving such a problem becomes particularly pronounced when working with today's largest and most capable models such as GPT-4 and Gemini. These are black box models, meaning that their internal mechanisms are completely inaccessible to us. We cannot inspect their weights, their intermediate activations, or the reasoning trace that lead to a given output. In practice, we interact with them purely through an input-output interface called API call. We provide a prompt and we observe a response. As a result, optimizing their behavior becomes a non-trivial search problem. Let's start by framing our problem. We are interested in optimizing instructions for a large language model that we treat as black box, meaning we can't access its internal weights or gradients and it's only accessible by its output. Formally, our goal is to find the instruction denoted by tau that maximizes the expected performance of the model across a validation set. Here, F represents a black box model and D is our dataset of input-output pairs X and Y, and Q is a score function measuring how good the model's prediction is compared to the ground truth. In other words, we are trying to find the instruction tau that, when combined with the task input X, yield to the highest average score Q. However, this optimization is non-trivial because we don't have access to the gradients from the black box model and the space of possible instructions is enormous and discrete. So, how do we solve this? That's where our approach ACING comes in. This slide shows our framework. So the left red box represents our actor-critic agent and the right blue box represents the environment. Here is what happens step by step. The actor outputs a soft prompt vector which is projected into the embedding space. And we obtain our soft prompt D. This soft prompt concatenated with task exemplars are then fed to a white box LLM, which translates it into a discrete human-readable instruction tau. That instruction is used to query the black box LLM. The black box model processes the instruction with the task input and produces its output. A score function then evaluates these outputs and produces a reward signal. This reward goes back to the critic, which updates the policy to make the next instruction more effective. Importantly, both LLMs, the white box and the black box, remain frozen throughout the process. Only the small networks actor and critic are learned. Through this iteration process, ACING effectively learns to navigate the huge instruction space and discover prompts that maximize the black box model's performance. Let's look at this simple example to understand better how our framework works. So this example represents the larger animal example, which means given two animals, we want to output the larger animal. So here the actor will suggest an action, would be projected to obtain a soft prompt, and we have exemplars. So the exemplars are a set of input and output examples. This set would be fed to the embedding layer of the white box LLM to obtain an embedding, and this embedding would be concatenated with the soft prompt and fed into the rest of the layers of the white box LLM. The white box will generate a human-readable instruction, which is, in this case, the instruction was to create a program that takes two animals as input and outputs the animal that is bigger. This instruction concatenated with a validation set would be fed to the black box LLM, which produces a prediction. And as we have access to the ground truth, a score function would be computed and it would be served as a reward function. Now, let's look at how our learned instructions compare to human written ones. This table presents a qualitative and quantitative comparison across several linguistic categories. On the left, we list the category and the task. The middle columns show the human instruction versus instruction generated by ACING, and the two columns on the right report the corresponding performance scores. You can immediately see that the instructions produced by ACING are semantically meaningful and task-aligned. Interestingly, for Rhyme, ACING discovers a novel but effective phrasing that yields to a perfect score of 1, and outperforming human instruction. Overall, these examples demonstrate that ACING can autonomously generate clear and functional instructions that rival and even surpass carefully designed human ones. Now, we move to the quantitative comparison against baseline methods across a diverse benchmark of tasks. Here we compare ACING to APE, EvoPrompt, which uses evolutionary algorithm, Instruct0, which uses Bayesian optimization, and Instinct, which uses neural UCB. Each number represents the average task score with the best result bolded. What stands out here is that ACING achieves the highest median score of 0.69, outperforming all other baselines. It also ranks first on 13 tasks, which is nearly double the best performing competitor. If we look closer, ACING performs strongly on tasks involving structure and reasoning, like cause and effect, common concept, and word sorting. Here, we evaluate the importance of the critic network in our Actor-Critic framework as an ablation study. To do this, we compare our full ACING model with a simplified policy gradient version that removes the critic and directly updates the actor from the raw rewards. If we look at the result table on the right, across a wide range of tasks, the full ACING model achieves consistently higher or comparable scores. The median score rises from 0.70 without the critic to 0.71 with the critic, and more importantly, the number of best performing tasks increases from 14 to 21. We see that the critic's advantage estimates stabilized learning, especially for difficult or high variance tasks such as word unscrambling, cause and effect, and odd one out, where the policy gradient variant struggles to converge. The next ablation studies the effect of the number of exemplars used to condition the white box LLM when generating instructions. We compare ACING trained with only 1 exemplar per task against the main configuration, which uses 5 exemplars. The pattern is very clear. When using a single exemplar, the model's median score drops from 71 to 0.67, and the number of best performing tasks falls sharply from 24 to 11. Tasks that require higher level of reasoning or computational understanding, such as cause and effect, word unscrambling, and auto-categorization, benefit substantially from having multiple examples. On simpler tasks like spelling or translation, the difference is smaller since these tasks require less contextual diversity. In short, providing more exemplars allow the white box LLM to generalize better and produce more consistent instructions, giving the Actor-Critic agent richer feedback to learn from. In this slide, we present the reward conversions across different tasks. For all experiments, the budget of API calls was fixed to 165 following prior works. As shown, our method achieves its optimal prompt well before reaching the budget limit, demonstrating efficient conversions and stable reward improvement throughout the optimization process. To conclude, we introduce ACING, an actor-critic framework for instruction optimization in black box LLMs. By framing the problem as a continuous action RL task, ACING efficiently explores infinite instruction space using only black box feedback. Experimentally, ACING outperforms all baselines and even surpasses a human written prompts in 76% of tasks, achieving higher significant gain across instruction induction, reasoning, and summarization. Overall, ACING offers a general, efficient, and scalable solution for automated prompt optimization, a step toward autonomous instruction learning in black box models. Thank you.